Thank you very much for the kind introduction, the invitation. It's really great to be here. It's my first time here in St. Petersburg, and it's a very hospitable city. Thank you very much. Now, I'm a bit embarrassed because Professor Lipschitz asked me to prepare a very accessible talk, so essentially for students, and that's what I'm going to present. So this is some thoughts about coupling for people who don't know what it is, and I hope not too many know what it is. Otherwise you will be very, very much bored. Okay, it's about the coupling method. And the coupling method started somewhere in the 1930s with Döblin and became very fashionable about 30 years ago again. And it's a very powerful method, and I want to show you some applications. So, and of course the definition. So the first question is, what is coupling? And I want to give an abstract definition which looks like this. Suppose you have two measures, maybe probability measures, but it could be measures, on an abstract measurable space, which is at first finite dimensional, and later on we can take it infinite dimensional. And then we take rho, a further measure, on the product. And this is called coupling. With mu and nu as marginals, if mu and nu appear as the coordinates, so let's say a times e on this box, this is nu of a, and on the other side we get mu of b, for all a and b measurable. I've taken here the same spaces. This is not really necessary, but it makes it a bit simpler at the moment. And there are a few remarks, of course. The first remark is, there is always a coupling. And unfortunately, it's primitive in some sense, namely you just take the product construction. This will do the trick. What is more interesting is that we can have an interpretation in probability, namely if there are probability measures, we can construct random variables. Let's say x has the law mu and y has the law nu. The coupling, rho, would be the joint law of something which you should write as x prime, y prime. You can't really write x and y, or you shouldn't, where x prime has the law of x and y prime has the law of y. And here you see exactly what's going on. This is boring because if rho is mu times nu, this would correspond to the fact that x prime and y prime are independent. So you just would take an independent vector. So the idea is really to fill the things what happens between mu and nu, the interaction. And to see what you can do, let me make an example, which is really nice because it's easy to understand. And at the same time, it shows the power of the method and some somewhat surprising result. So the example I want to give is something most of you will have seen. Let's look at the binomial law. So the usual binomial distribution. K choose n, p to the k, 1 minus p and minus k. So the probability to get k successes in n draws with success probability p. And let's look at the Poisson law with intensity lambda. So that would be e to the minus lambda, lambda k, k factorial. And there is one result which is taught at every discrete probability course. It's the following theorem, which I would call the law of small numbers. And it essentially says, if you're interested in the binomial distribution, and if p is small and n is large, then we can safely replace it by the Poisson law. Now, to express this, usually one writes lambda is np. So you see here a trade-off. If n is big, p should be very small. And let's write it like this. This we need to make a bit more precise. And more precisely, what we want. So if you look at bk, n, and now to get this, obviously p should be a pn. This, then we send n to infinity. This converges really in a pointwise fashion to the Poisson law lambda n. And lambda n is npn, and the condition we need, that's the smallness, is embodied by the fact that this limit exists and has a limit between 0 and infinity. That's the precise statement. And what I want to do is I want to prove this theorem.
What is bk? What is k?
This k?
bk?
bk, that's the binomial law. It's over there. So it's k successes in n draws with probability p. Yeah. It's just, so to speak, the probability to have k successes. And
so it's not the convergence of the law, but just
but I'm going
of probabilities.
Exactly, it's the conversion of the probabilities, and we will see that you will get the convergence in law if you do the proof in the right way, and that's exactly the point. So the classical proof here is normally you take Stirling. So you take really the left-hand side, bk and p. And you observe that n factorial is something like 2pn square root n divided by e to the n. And then you have a few calculations and you get essentially that. That's the usual proof. What I want to do here, I want to do it a little bit differently. My idea is to use coupling. Now, what are my marginals? What are my x and y's? So first of all, to save a bit writing, I say p is pn. So I suppress the n. In the writing, but of course it should be always there. My xj's are Bernoulli random variables, so 0, 1 with probability p and q. And I assume they are IID. And the yj, they're going to be Poisson with parameter p. Same p here, they're also IID. And j is from 1 to n. Then I introduce the partial sums. and the Pn are the y1 plus the yn. And my task is now to find a good joint law. So find xj prime and yj prime joint law, which is good. And here you see the whole problem with coupling. You have to find the right coupling, not just to make here an independent vector will by nothing. So what I'm going to do is I draw you a table. Then you see immediately how to take it. Up there I say yj can be 0 or yj can be 1, 2, 3 and so on. Here xj prime can be 0 or 1. Now what do I need as a marginal? I'm 0 with probability 1 minus p. I'm 1, a success with probability p. And on the Poisson side, to be 0 is e to the minus p, and to be 1, 2, 3 and so on would be p to the k divided by k factorial e to the minus p. And the trick is now really to fill the 4 squares that you get exactly these marginals. What I'm going to do is I take here a 0, here a 1 minus p, here a e minus p minus 1 minus p. It's a little bit like Sudoku playing. And here, for the k case, like that. And what is easy to see, if you sum it up, you get exactly these marginals. And here, my row, that would be my row from above. Of course, I have many, many choices for that. But this, you will see, is a clever choice. And let's see what we can do with that. So first of all, this fits the bill for a coupling, yeah? It's a coupling of those two random variables. And let's see what happens if I sum them up. So what I'm really interested in is the probability that Sn is k. This would be my binomial probability. And I subtract from that my Pn being k. That would be my Poisson approximation. I want that this goes to 0. Then the theorem is finished. And what the advantage now is, those two don't need to live in the same probability space, but the prime random variables live on the same probability space because I've constructed them to be on the same probability space. So what I do here, strictly speaking, I have a new probability measure, and I look that Sn prime is k, and I subtract from that Pn prime is k. So far nothing's happened, but now I start to play. Because I'm on the same probability space, I can look at the probability that Sn prime is not Pn prime. And of course, I should add here plus Sn prime is Pn prime. But this I can leave away, because if Sn prime is Pn prime, I could replace the Pn prime by an Sn prime, and this goes. Okay, fine. Then let's take the modulus. Also good. And now comes something interesting. I can even sum. I can sum over all k. And what I'm going to show is, I'm going to show that the whole sum goes to 0. Not just a single member, but the whole sum is going to go to 0. Now, the first thing is I make a rather crude estimate by using the triangular inequality here. So I estimate that by the sum k of p prime Sn prime is k. Sn prime is unequal Pn prime, and the sum p prime Pn prime is k. Sn prime is not Pn prime. Okay, what is nice here, you have here a complete distinction of all cases. This sums up to 1, that sums up to 1, and what we are left with 2 times p Sn prime is unequal Pn prime. Okay, of course, p prime. And now we go to the table, because we can really see when this happens. Now, Sn prime and Pn prime being unequal means, since Sn was the sum of the x's and the Pn was the sum of the y's, and same here, of course. This happens certainly if one pair is unequal. So we can, again, rather brutally change that to the probability that xn prime is xj prime is unequal yj prime to n. Let's have a look when this happens. This happens exactly in the case here. So they can be both 0. That's in some sense a bad case. The good case would be here and here. So what you would get is, we say this is 1 minus that they are the same. Okay, and they are the same on the diagonal. So this is p times 1 minus e minus p. Yeah. So 1 minus both 0 minus both 1. Okay, and this we can estimate by a p. Yeah, because usual convexity estimate, you estimate it by a p square. Okay, that means we have here 2 times n times p. And don't forget, the p was a pn. Here I write it again. Okay. So, yeah, that's important. Thank you. Thank you very much. Now let's see what we've got. We've got that the sum k is 0 to infinity of the probability of the binomial Sn is k minus the Poisson is estimated by 2 times n Pn square. And let me write that as 2npn times pn. Now the square is of course important, because this goes by assumption to 2 lambda. That means this goes to 0. That means the whole thing goes to 0. Okay. That's the end of the proof, only that we've proved something much more, because what we've seen here, we have here actually what is usually called the total variation distance. Okay, so it's a much stronger result. You get even a speed of convergence, and to get, with a relatively simple proof, much more than you've bargained for. Now, let's have a look what actually happened. And let me cut out the essential part of that proof. So that's the next question, section 2. What happened? Now, what I've used here, or what you see here, is what people in coupling call the so-called basic estimate. And this works like this. Suppose x and y are 2 random variables. Need not be the same probability space, but let's say the same state space. And suppose there is the coupling. And let me write that as x prime, y prime. So there's a joint distribution, but the marginals are x and y. Then the probability x in some set minus probability y in some set modulus total variation distance, I'll tell you in a sec what it is estimated by 2 times. Now, this lives in a new probability space where those two are unequal. That's exactly what we've used here. And total variation is nothing but the soup over all measurable sets where px is in A minus y is also in A. So it's the worst case scenario in some sense. It's a distance on the space of, in this case, probability measures. What is funny, the same proof I've showed in the simple case works here. And the main point, I will show it to you in a sec, the main point is that x prime and y prime are the same probability space. So we are playing here actually not only with the random variables, but with the fact that we deal with one probability space where we can realize both variables in a good way. And the proof goes really like that. We start with px in A minus py in A. Just as you can see above, I write it on the new probability space. X prime is in A. And subtract y prime in A. And then I observe that I can put in here x prime unequal y prime, because if they're equal, we have a 0. Yeah? If they're equal, I can replace that y prime by an x prime, and I have left and right the same thing. Now we take the modulus, take the triangular inequality, and rather than summing up, I throw this away. here we are. And the only thing that's independent of A, now we take the soup. So that's the proof. But where comes the coupling in? I mean, this would all work with the independent coupling as well. The main point is the type of coupling we use gives me control here. Yeah? Control via the type of the coupling. And if you have independent coupling, usually nothing comes out. So independent coupling is good for existence, proves that you have coupling, but for not much more, honestly. Okay, now let's go one step further. So this gives you an idea of what coupling can be. And I want now to go to random walks. Very simple situation. I take a random walk in ZD, so in the d-dimensional grid. So the setting is as follows. We take really the simplest possible situation. We take size. We assume they are IID steps. And I even want to have a simple random walk. What I'm going to say works for Markov chains. Yeah, but later on I want to have an example with simple random walk, so let's stay with a simple random walk. And simple random walk, by that I mean that if you look at the step distribution, then you can go in each unit direction. EI is the ith unit vector. You're going up and down along that vector. And this is, of course, 1 over 2D. Fine. And then you construct your random walk. Xn, you take a starting point, little x. Let's take it deterministic. And then you add up the steps. And Yn just signifies that I take essentially the same random walk, but at a different point y. I'm a bit sloppy here. You don't really take the same random variables, but you, strictly speaking, take copies. And what I'm now interested in, I'm interested in the time where those two meet. So it's the infimum of all n in n, such that xn and yn coincide. So the primes, again, are IID copies of the xij's. So I have two independent random walks at different starting points. And I ask, when do they meet? That's the meeting time. And of course, this may never happen. In this case, I have the empty set, and the empty set has the inf plus infimum. Now let's suppose they meet. What happens then? Now, first of all, suppose there is an x, and there is the y. Then my random walk goes somewhere on the grid. And let's say they meet at that point in finite time. Let's call that tau xy. And after that, it's usual to continue them with one set of xi's. So in some sense, the paths after that are seen to merge. Before they are walking in a different way, and then after the meeting time, they merge. But the first question is, when can it happen that they meet? And if you think of a simple random walk, it's clear that one necessary condition here is that x minus y is even. If they're odd steps away, they can't meet, because they always avoid themselves. What do I mean by even? So by that I mean actually you take the coordinates and the number that comes out should be an even integer. That's necessary for meeting. Okay. Now, let's go back to coupling. And a coupling would be a realization of those on the same space. And since I'm already in the same space, there is no need to go to a new probability space. But you can use the basic estimate, as I've shown it, and you get the following thing. What I'm going to do is make an observation. If you shift your random walk, let me call it Z. So this would be Z of K in N0. And the shifted random walk would of course start at Zn. This is again a simple random walk. Just started at a later step. And now observe that if you shift xn and you ask when it's different from the shifted yn, this is exactly the time that n is before the meeting point. Because with this convention, after tau, they meet. So, yeah. Okay. And that means that we get immediately lemma prime, and it says in the above setup that the probability of the first random walk shifted in some set minus the second random walk shifted in some set. Then you look at the total variation distance. It's less or equal than 2 times p coupling time bigger than n. Or another way to phrase that, you could say, okay, my xn is z. Now I just look at the nth instant, yeah? I'm not really interested in all total variation, I'm just interested in the nth instant. So I throw away a lot of these functionals here. I take the sum over all z. And then I can still bound that by this. Okay. And now the trick, and that's what I'm after, what I want. I want that the right-hand side goes to 0 as n goes to infinity.
So how can I pass from this, from the above inequality to the lower one?
Because you have here the whole tail. So you just are interested in, I mean, this is a big cylinder set. So you just take one z and there is a trick. The point is you're free in the sets you put in there. Yeah? And what I do is I have here just singletons. That's the main point, yeah? So what you take here, you have here the soup over all sets here. And you do the first thing, you just take one element from the shifts because these are cylinder sets. And then you take here just singletons and observe what you do. You take A is RD and split it. I mean ZD, sorry. And there you take the nth component, or in this case the first component, yeah? Because this is a set that lives in A1 times A2 and so on. Then you can split it with a simple triangle trick to get that one. We can do that later on. It's relatively easy. Okay. Okay. So we want that this is 0. And in order to get that, what we need is that tau xy is finite almost surely. So we have to find a coupling where we can realize the coupling in a finite time. And that basically means how can I justify such a picture? The question is, how can I make the paths meet? There's a simple trick, and it's a beautiful trick. The main point here, again, is that in principle, I'm free to choose my psi prime as long as they have the same law as psi1. It's a bit misleading to say that these are IIDs, copies of the psi j. What I meant by that is that psi primes, they are independent among each other, but of course there is going to be a relation between psi1 and psi1 prime. And this relation I want to exploit in coupling. So the idea is the x is given, with a yn, the y is given, and I want to have just steps which have the same law as the original steps, but dependent. And let me show it in dimension 1. So the idea here is I take x, and then I have a y. And what I do is I take the midpoint. Because x and y are even, I can take x plus y half. And whenever I make a step up here, I take here the opposite step. So I really reflect at that line. So there would be 2 down. That would mean 2 up here. Up, down. In the end, they would meet in that plane or in that hyperplane. Tau. And why is tau almost finite? Because my random walk oscillates. It's recurrent. So we meet dimension d1 oscillates. Okay. So my coupling Zn would have the starting point x, y as a pair, and my step zeta 1, so Zn is Z0 plus zeta 1 plus zeta n, would be psi 1 minus psi 1. And here I take really the same with a negative sign. So they're definitely dependent, yeah? That's very important here. And this is, again, a random walk. Not a simple random walk, but a random walk. Okay. Now that works in one dimension. It also works in higher dimension, and let me sketch that. What you do here. So, if I have dimension 2, there are 2 cases. Again, we start with x and y. Case 1 would say x1 minus y1 and x2 minus y2 are both even. Then what we do is we do this procedure twice. In each coordinate. And we just sum the coupling times. There may be faster methods, but in this sense, they meet. Second case, well, both are odd. Okay. And here, it's a little bit ugly to write it up formally, but the idea is simple. We do one step. And now let me add for the induction later on. Do one step in the not yet coupled coordinates. And in this case, we would say wait for first step in the not yet coupled coordinates, but here you move immediately and then swap in the coupling, swap the coordinates. Okay? So the first coordinate becomes the second and the second becomes the first. The consequence is we are back in 1 from that point on.
I Why just don't make independent just a usual step, and then with positive probability you just go from 2 to 1?
No. If you do a step, you stay always odd apart. You have to make what I want is that we are...
No, not the same step. I mean independently on x and y. You have two processes. You just let them do they work independently. They with positive probability you just go from 2 to 1.
That would be also a possibility, but that's the standard way. I mean, you just make one step and you swap the coordinates from that point, which you can do, and then you're even apart. Didn't think too much about it. This is actually the standard way to do it, and your method probably would also work. I mean, the main point is that I have to get with these in the even regime, and then do the coupling. Yeah, and if you have d coordinates, you deal first with the cases which are even, then you know there are even many odd cases, and then you make them into pairs and you this trick again and again. So anyway, this is one way how you can couple, and you see your colleague just make a suggestion which might be easier to get that in the even into the even regime, but we just need one way. So the main point is that we can have the same upshot. The probability that tau x y is finite is 1. And that's all we need, because then we can make sure that this goes to 0 as n goes to infinity. Okay, now let me show an application which I had in mind. Don't know how far I get with that. What I want to do, I'm interested in the Dirichlet problem. This is usually considered for the Laplacian, but what I want to do is I want to have it in a discrete setting. So it's essentially linear equations, but there's a twist to it. So what is the Dirichlet problem? In a discrete setting. So what we have is a set A in the grid. And what I would call the boundary of A, these are all points which are not in A, but such that x minus A has a distance 1 for some A in A. So essentially, if that's your set, your boundary would be these points. Yeah, that's the boundary. And now I need the discrete Laplace operator. Now, the discrete Laplace operator is 1 over 2d, and what you do, you sum all vectors of length 1, so these are the unit vectors plus or minus, u x plus e minus ux. Now, this looks like a gradient, but it's not, because you double here, so if you write that explicitly, you get 1 over 2d, I is 1 to d ux plus ei minus plus ux minus ei minus 2u of x. So you see there's actually a second difference, and that is, it's really some kind of Laplacian. And what is interesting now is that here the random walk appears, because you can write this as the expected value of a random walk starting at x, making one step, subtracting the starting point. That means the probability x that x0 is x is 1. Okay, so this has a probabilistic interpretation. And I'm now interested in another random time. I'm interested in the time where my random walk starts in the set but leaves it. So I start in my set A and I want to exit it. It's the same to hit the boundary. It's exactly this, the same setup with Brownian motion. So if one looks at a continuous time case, this has a complete analogy up to now. And I'm interested in the solution to the Dirichlet problem, which I will formulate in a second. So the problem is the following. Suppose A is bounded. Then the Dirichlet problem which I want to call dp, is Laplace u is 0 inside my set, and on the boundary I have a prescribed function. So here x is in A, x is in the boundary. Has a unique solution. And what is nice, I can write it down. What I do is I start my random walk in X, and then I take the time where I exit the set. And here X is from A bar. And of course, if I exit outside, tau is 0 if X is not in A bar is as usual that. And in this case, this is both constructive as well as representative. In the Brownian motion case, you need to assure that you have a solution and then you can represent it. But since this is a nicer case in some sense, the proof of that is constructive. And it gives you a nice formula for that. So the idea here is, let's say I take A in A. And let's look at U of A. This is, by definition, EA of F. Oh, sorry. It must be an F because I start on the boundary. F of X tau. And now I observe one thing. Since I'm starting inside, I must make one step to leave. So this is really the same as f of x tau, and tau is at least 1. And now I use, you could say, the strong Markov property, but you can also say just make one step first. So one step principle, what I do is, let me do one step. That brings me to a new starting point, which is the thing after my first step. But then I still have to exit. So it's the same tau, only starting at x1. This goes away because I've done my step. And then I do my averaging, which goes here. Yeah. This E goes there. And that's still the randomness left. And if you look at it, this is just EAU x1. And if you bring it over, you get the first line here. And the other half is actually even easier. So if I want to start outside, it's easier. Okay. So this is a very quick proof of that. But the main point here is I can do this only because my set is bounded. So attention, tau is finite as A is bounded. Otherwise this proof wouldn't work. Yeah? With unbounded A it doesn't work. And this is the case I'm interested in and where coupling can be used. And let me do that now. The theorem is the following. Now, A is any set. Let's say it's connected. And let's suppose that my F is bounded. The boundary is not bounded, but this thing is bounded. Bounded function. Then the theorem runs that all bounded solutions to the Dirichlet problem, A unbounded, boundary data bounded, are of the following form. Well, there's one part you know. That's the one we've seen. But only if tau is finite. Okay, so this one can believe. What's the second part? That's some arbitrary constant and the probability to start in X and tau is infinity. Now, just as in the previous calculation, one can check this solves the Dirichlet problem. And it's essentially the same calculation. The main point is that we get really all solutions in this way. And let me just briefly sketch the 4 steps and then I stop. The first thing is we can assume that f is 0 without loss of generality. That means we can forget about this part here and we have to show that all solutions to this Dirichlet problem are of that type. The second step is a martingale trick. So what you do is you take your u x n minus x minimum tau and you observe that if you're a solution, you can subtract a sum as long as k is less than n minimum tau of delta u xk, because this stuff is all 0. Yeah, this is before we exit, and this one can show is a martingale. what this is essentially, this is Dynkin's formula. In a discrete setting. And since it's a martingale, we can get our hands on the expected value. And what we get, that u of x is just the expected value of x minimum tau at 0. That's trivial. But since it's a martingale, it's the same as this. And this is the same as x and minimum tau if tau is bigger than n, because if tau is less or equal than n, you get a 0. Okay, and finally, 2 more steps. You can write u of x with this as u of xn, because n wins here. And now let me make 2 steps. Yeah, I take n is 2k. And I subtract u xn, what is remaining, less or equal. Okay, this is just, 2k is just such that n is bigger than that, because I want to send n to infinity. And this part I call j. And this I can represent in the following way. 2k. And I take here a conditional probability. Conditioned that tau is bigger than 2k minus jx. And this I call ix. Okay. And the last step is, now comes coupling in. It's really the last step. Ix minus iy goes to 0 as n goes to infinity. And jx minus jy can be estimated in a trivial way by just these probabilities and some big constant. X 2k less than tau less than infinity. And for x, and then the same for y. Okay. Good. And if you have that, you can conclude, but these were pretty fairly direct calculations. At that point, we need the coupling in the form of the sum, which I've written down. And the last step is that you get that u of x is cx tau is infinity. What you do is you send k to infinity. Okay. And then you need one more step to discuss the x away. That's a harmonic argument, which I'm not going to do now. But what is surprising here is that it's relatively hard to show, already in this simple setting, in an unbounded domain, that all solutions are of this form. That these are solutions is easy, but that these are all of them is really the hard bit, and the hard bit is the place where my random walk actually never leaves my set. On the other hand, this is a beautiful theorem. Usually it's proved with a local limit theorem, and the coupling part is a little bit hidden in here. So sorry if I was very sketchy here, but that's all I wanted to say.
Thank you very much. Please, questions? Comments? So coupling is hidden somewhere, which...
Yeah. The main problem here is that if you look at the structure of the I and the J, you see you get differences of different starting points. And at some point you have to make sure that you can dominate sums of the type sum p starting at x and xn having a value minus p starting at y and xn having a value are small. That's exactly the sum where you asked. This sum I must get small. If I can control that, that's fine. At that point it's used. And as I said, usually they use so-called local limit theorems to prove that, but coupling is more elegant.
So what did you prove about this coupling of random walks? I cannot make a resume.
Okay, what I showed here, I gave a sketch that if you use coupling by reflection, that the simple random walk has a finite coupling time.
Yeah, this one-dimensional case is...
The one-dimensional is, yes. And in 2 dimensions, the idea is to couple it in each coordinate. And there you have 2 cases. The case one...
What did you prove? Not how did you prove, but what did you prove?
That the coupling time also in a d-dimensional random walk can be finite if you use coupling by reflection.
Okay, so you constructed a coupling which works in arbitrary dimension.
Yes.
This was the point.
Yeah, that was the main point, yeah.
Independently of whether it is dimension 2 or bigger than 2.
Yes, works in all dimensions.
Okay. This is sometimes sensible.
No, this is really the essence.
Between dimension 2 and higher than 2. Okay, thank you. Any other questions? Okay, if there are no questions, let's thank the speaker again.